topic is postulates. Okay, postulates of special theory of relativity. So it's postulates of STR. I'll just write down STR, special theory of relativity. So this is a very important question, and the postulate actually comes in from the Maxwell's equation. Okay, whatever we have learned in Maxwell's equation, from there itself we are actually going to get one of the postulates. Okay, but before that, whatever we have learned in Galilean transformation, that is actually one postulate. So you will get this statement more or less everywhere, and you are going to, more or less use this answer if I'm asking you a question on this. Okay, all the laws of physics. Okay, so we consider it to be the Maxwell's equation or the Newton's law. All of them, okay, are valid in any frame of reference. That's the first postulate. Okay, are the same in all inertial frame of reference. So this term is very important. Whenever you're writing down the postulate, don't miss out the term inertial. Okay, all reference frames. So this is the first postulate that you should know. Okay, so that means in the last class we saw that there is nothing like non-invariance of Maxwell's equation. Initially it was thought that there was non-invariance, but later on, since the speed of light remains same in all frames of reference, even Maxwell's equation is the same in all frames of reference. So whatever laws of physics you consider, be the Newton's law, gravitational law, okay, or the Maxwell's equation, everything is more or less same in all reference frame. But the important point is it should be inertial. It should move with a constant velocity. It does not have any kind of acceleration involved. That's the first postulate. And the second postulate is something which we have seen in the Michelson-Morley experiment, and that states that the speed of light, okay, so usually we denote it as c, okay, speed of light c in a vacuum here also it will remain 3 into 10 to the power 8 in all frames of reference. Okay, so if you are just confused, what exactly was the experiment all about, the experiment was only proving that the speed of light remains same, okay, in whichever system you basically consider. Okay, be it a moving frame or a standstill frame. So in vacuum it is 3 to 10 to the power 8 meter per second. You might have a very dense medium where the speed of light will be, let's say, lesser than this. But then if you have that same dense medium moving, the speed of light will remain the same as it was in the not moving system, okay, or in the unprimed system. So this is important. So in a vacuum is the same. In, again, here it's important, we use the term inertial, okay, in all inertial reference frame. So these two statements are actually important, and this will be basically a 1 or 2 marks question. If explanation is asked, it can be a descriptive question, but then I think you can explain it also. So inertial frames, regardless, okay, of the motion of the observer or source, regardless of the motion of the observer or source. So whether the source is moving or the observer is moving, the speed of light will remain 3 into 10 to the power 8. So these are the two postulates of a special theory of relativity. Okay, and this is something which we have built into. Okay, for the last 3 classes, whatever we have learned, we have seen that yes, this is true. So we are going to talk about Lorentz transformation equation today, and for that let me start on a clean slate. Okay, and I will tell you why the speed of light actually affects the result. Okay, so the derivation for today is, I hope I'll be able to finish it. If not, then probably we'll continue in the next class. But this is actually a long derivation, and we are going to see that whatever we have seen in Galilean transformation is not the same as in Lorentz transformation. Okay, it's going to be different. So today's class, the main thing is Lorentz transformation equations. So before we start, okay, we have to understand certain things here. Okay, Let me tell you this. Imagine, okay, imagine, you basically have a relation between x prime and let's say x. Okay, so we have already seen the relation, okay, which is nothing but x minus vt plus vt and so on, okay, depending on what frame of reference we are considering. Okay, now what does it mean that if I basically consider two frames of reference, okay, and basically consider a position here p, okay, and this may be having a coordinate, let's say x prime, okay, and let's say y prime, two dimensional coordinate, and maybe it's x and y. Understand this. So that means if I consider this to be the prime unprimed coordinate and this is the prime coordinate, from here to here we know it is x prime, we have seen in the last class, and here to here it is x. So that means this relation that we basically have is having one result where the distance is either x prime in prime coordinate or x in the unprime coordinate. There cannot be two distances, there will be only one distances. Okay, similarly if I basically say I have a relation, let's say this is something which I don't know, and I say that x is equal to, let's say, x square minus vt. I'm just saying, let's say, imagine. That means that for one value of x prime, you are going to get, because it's a quadratic equation, you are going to get two solutions here. You're going to get two solutions, okay? Forget about that one value. Since it's a quadratic equation, if we are considering mathematically, you are going to have two solutions. That means if in one frame of reference we have got one distance, in the other frame of reference, let's say if the relation is, let's say, x prime is equal to x square, and let's say I say x prime, I know it is 2 centimeter in the prime coordinate, so this is x square. That means in the unprime coordinate this would be plus 2 and minus 2. That means I will be having a distance on this side as well as I will be having a distance on this side. Now this is physically impossible, because for the same particle I cannot have two distances, but mathematics says that there should be two distances, and hence what we can conclude is that whatever relation we are basically considering, be it in Lorentz transformation or Galilean transformation or any transformation system, the relation should be more or less linear. That's the importance of linear relationship. A linear relationship tells me that for one value of x prime I will have only one value of x. But if you consider a quadratic equation, okay, maybe a binomial equation and so on, you'll basically see that there will be two, three solutions for the same value. But distance cannot be two. There can be only one distance. And that's the reason we are basically considering it to be a linear relationship. Now the problem here is, as I said, that this v is something which is comparable to, something which we see in our daily life, but not comparable to the speed of light. So we have to write down a general form when we actually try to understand Lorentz transformation. So what we do is, let's start the derivation here. This is just for your understanding, okay? Just keep this in mind, take it as a note. Let x prime is equal to ax plus bt. So this is the relation. Why? Because when we talk about the relation of x prime and x, okay, we know that this x prime should be a function of x in the unprimed system and time t. So if we want to write down a linear relationship, we can actually write it down like this: x prime is equal to ax plus bt. Now you'll say that we have already done this. Why I'm writing this? Because I'm saying, let's say I don't know what is the dependency of x prime on x and t. I don't know what is the variable here. So I've just taken a general variable x and t. Oh, sorry, a and b. Okay. So this is basically a linear relation. So I hope we all understand this and we agree that this is a linear relation. And why we take a linear relation, although you really don't need to explain it in exam if I'm asking you a descriptive question on the derivation, but I think you should know why we are taking a linear relationship. If we take a quadratic, binomial, whatever relation, you're going to get two solutions, which is actually not true, cannot be possible physically, right? So this is one relation that we have, and let's mark this relation as relation as 1. So we'll take this relation as 1. Okay, so this is the first relation and we are going to start. So now you have to remember, okay, whatever I'm going to derive, you have to be observe it carefully and try to understand it. Okay, now what is our aim? Our aim is to calculate, okay, we have to calculate A and B, A and B. Okay, and if we are able to find out what is the value of a and b, we know what is the relation between x prime, x and t, so we are going to do that now. Okay, and what about y prime? So we are going to assume the same thing, that y axis is coinciding and not moving, and z prime will remain as z. But now time is important, because if something starts to move at the speed of light, there will be something which is called the time dilation, which will come into effect. So time, I really cannot say that if I measure the time on the primed frame, it will the same as t. Okay, this would be wrong here, because we are assuming that this is moving at the speed of light. So that means for time also we have to take a relation. So here also we are going to take a linear relation. Let's say I will take it as tx plus f of t. So that means we are basically having four unknowns here. Okay, so the aim is we have to find out what is a, what is b, what is d, and what is f are unknowns. You can take anything, even if you don't want to take d and f. D I have taken, I have not taken c, because c will be denoting speed of light here. Okay, so we are not going to do that. Okay, now what we are going to do, we are going to consider some events. Okay, so let's do that. Consider event. So I gave you a very clear idea what is event. So something happening, maybe the flashing of a bulb, x, y, z, okay, at time t. So I'm considering these dimensions here, x, y, z, and t. Okay, so that is the event that we are going to have. Now if I can take any kind of figure, but I will prefer taking these kind of figure. Okay, let me just rub this out. Okay, so that we can do more on the same page. Okay, so what happens usually is I am going to consider two frames of reference here. Okay, maybe I will consider two frames of reference here. See this is one frame of reference. Okay, S frame, and let's say I'm just moving along the x-axis. There is no motion along y or the z-axis, so I can take this. So maybe this is moving at a velocity v, and this velocity v is very high, but right now I'm saying that okay, this is just velocity v. Okay, and let's say this is my prime frame and this is my unprimed frame. So this is the S frame and this is the S prime frame. Okay, so if we just consider the time, okay, so let's say at time t, okay, that means we are measuring it from the unprimed frame. Okay, that means I can just simply say in S frame. You can write down the exact way I'm writing. Okay, I think there is nothing more to be explained here. In S frame, what is my x? So if I am having this entire frame of reference moving and I want to measure what is this position in time t, I know that this distance that it has covered is nothing but v into t. V into t is the time. So I will just take x is equal to v into t. If you're confused, just stop me, I'll explain again. X is equal to vt, and then y is equal to 0. There is no motion along the y axis, and then z is also equal to 0, and time is t. I'm not saying what's the time, I'm just saying that the time is t. Okay, this is in the S frame. Okay, so similarly I can also consider for the S prime frame. So I can just simply write it down as in S prime frame. Okay, so what happens in X prime frame? Okay, in the X prime frame we are going to have, okay, this X prime is equal to 0, because the point is, let's say, on the axis, and this is also moving. So let's say it doesn't have any displacement here, so x prime will remain as 0. I'm just assuming it. Okay, y prime is equal to 0, because I'm saying that the entire frame is moving. So y prime, there is no change, is 0. Z prime is equal to 0, but then there is a time, so I'll just keep this as t prime. Okay, so what happens is now we can actually play around with relation 1. So if we check relation 1, what does it imply? If I check for x prime, I know x prime is 0 from in the S prime frame. So I will just take this to be 0. Okay, and then I is equal to a into x. Now x is equal to vt. We have got it from here, considering the situation. A into vt. It's all algebra. Okay, you have to be very careful while doing the sum, and these steps should not be very difficult for you. plus b into t. Okay, we have it. So what we can do is I can take t common, okay, and we can have it as av plus b. This side we have 0, so time gets cancelled out. So we can just simply say it is av plus b is equal to 0. That implies that b is equal to minus of av. So this is one relation that we have already calculated. So we have the answer for b. That means b and a are connected, and this should be the relation that we have. Okay, so let's just keep this in mind. So if we take this, therefore we can again replace the value of b in 1. This is how you actually solve, conditional problems in maths. So you use one condition, find out the value of a variable, and then you replace it in the original equation. What was my original equation? X prime is equal to ax. So x prime is equal to ax minus, and then in place of b I'll write it down minus av into t. So I can just take a common, and then I can write it down as x minus vt. Similarly, we can actually write down for y prime, which is we already know is equal to y. Z prime is equal to z, and t prime we don't know. Okay, and we have already said that t prime is equal to dx plus ft. So I'll keep it as dx plus f of t. Okay, so we have these relations. Now what we are going to do is we are going to do a bit of conditional analysis. Okay, and let's do it now. Okay, so let's do it when, let's take some conditions here. It's a long derivation. Okay, so please be with me, don't get confused here. When o prime, okay, and o are crossing, that means they are in the initial condition. When they are crossing, that means for both of them the time can be considered to be 0. They have just started. Okay, when o prime and o are crossing, so I will take this as o, and maybe I'll take this as o prime. Okay, are crossing. Okay, and a light glows, and a light glows. So why I'm saying that, because that is the event that we are actually considering. And a light glows, okay, at where? At o prime. Okay, at, the frame of reference where we actually have o prime both together in all directions. In all directions. I will tell you what is the importance of this all directions and why I'm saying all directions, because if a light bulb goes off, that means there will be a light ray which has traveled at this point, there will be something which has traveled at this point, there is something which is traveled at this point. Okay, so in all the directions we'll basically have the lights. Okay, so that is what is happening here, and what we are going to do is we are going to analyze the situation in 3 different events. Okay, so we are going to start with event 1. Please remember, this is the easiest way to derive Lorentz transformation. So please remember the steps. What is the first event? Okay, so for the first event, what I'm going to do is, again, I'll prefer drawing a graph here. Okay, so maybe I can draw this, and then I can draw this, and we say that O and O dash are basically coinciding here. Okay, and let's say we basically have an event, and where we have the light here. So it basically has start glown here where we have O and O prime both, and the light ray has traveled here. Okay, so maybe I can just write one small line here. Okay, light has reached here. Okay, maybe so that it's a bit clear to you. Light has sorry. Okay, light has reached here. So the light has reached here. Now it's basically nothing but the speed of light. So we know that this distance would be velocity into time. This distance would be velocity into time. Since it's light, so the speed is c, velocity is c, and time is t. Okay, so this is the distance that it has covered, and this is the scenario that we have right now. Okay, so considering that situation, we know that x is equal to c into t. That's the distance that it has covered in time t in the x direction. Y is equal to 0, z is equal to 0, and time remains as t, right? Therefore we can again use the initial condition. We can write down x prime is equal to a into, see this, x prime is equal to a into x minus vt. We are going to build on that. Okay, in place of x, I'm going to replace it with ct. So it is ct minus vt. Okay, or maybe I can write down one more line here so that it's a bit better. So we can just simply write it down as a into x minus vt, which we got in the previous section. And then here what we can do is we can replace this x with ct minus vt. Okay, we have it as ct minus vt. Now we have got one more relation, and we can take out t common. So we can take a t, and this would be nothing but c minus v. Let's mark this equation. Okay, if we mark it, it's easy to track. So let me mark this as number 2. Okay, in a similar way we can also write down the relation for t prime. Okay, so t prime is equal to dx plus ft, and dx is nothing but c into t plus ft, and then we can take t common, and within bracket it would be nothing but tc plus f. Okay, and that's your relation 3. Please mark your relations carefully, okay, because we are going to use them. Okay, and there are so many relations that you might get confused at some point of time, so you just do these stepwise. Okay, so this is important. But since we are talking about the speed of light, whether you consider the unprimed frame or the primed frame, the relation for x prime is going to remain the same. Okay, that comes from the special theory of relativity. Okay, so that will be something which we are going to understand now. Okay, so but x prime is equal to ct prime. Okay, why we say it is the same? Because you know of relativity, right? Relativity, postulates of relativity rather. Speed c is same in all frames. Okay, so we have to keep these things in mind, because when we are deriving it we are going to use that postulate. So that means once the postulate was there, then only Lorentz was able to derive his relation, right? That's logical. So again we have got the relation as x prime, okay, is equal to at into c minus v. We already have it from the previous slide. Okay, that means I'll just mark it. If you are noting it down, this is from relation 2, from 2. And now we are saying that x prime is equal to ct prime, so you can just say this is ct prime is equal to at into c minus v. Okay, so maybe we can just write it as number 4. 3 we have already marked, so this is number 4, and then we can say we can divide 4 by 3. Yeah, any doubts? So what is 4? 4 is ct prime on the left hand side, and 3, which is the last relation that we have written in the last page. Okay, let's just check it once. This one, this relation is 3. On the right hand side, left hand side, it is t prime. So what I'm going to do is I'm going to write it down as ct prime divided by t prime is equal to, what is on this side? This is at into c minus v divided by, this one is t into dc plus f, right? So this is t into dc plus f. We are trying to reduce the number of variables and find out the relation between each of these variables, so that we can solve our problems easily. Okay, and then this and this will actually just get cancelled out. Okay, and on this side also this t and this t will get cancelled out, so it is left out with is a into c minus v divided by dc plus f. Okay, so what does it mean? Therefore we can just cross multiply with c, so I can simply write it down as dc square plus fc is equal to a into c minus v. So you have to be very careful with the steps. Okay, I definitely won't suggest you to remember these, because it's difficult, so many relations. You have to just know what will be the final result that you are going to get. Okay, so just keep an aim on that, and this is something which we are going to do. So this was about event 1, and from event 1 we have seen that there are three relations: this x prime, this t prime, and then we have a relation between this dfa. Okay, so we have these relations. Next, go for event 2. I told you there are going to be three events that we are going to analyze, and let's check now event 2. So what happens in event 2? Okay, event 2. Okay, let's see what happens in event 2. In event 2 it's the same. Okay, we are basically not going to move any origin here. We are not going to shift the origin. This is let's say your, just we are just drawing it. Okay, imagining that this is the scenario, and maybe this is the point where the event occurs. This is the point. Previously it was on this side, so this is CT. Now on the second point we have the bulb going off here, so it will flash along this direction, along this direction. So this is, let's say, the positive direction, so this would be the negative direction, right? But the distance will remain the same. It will be c into t. At the same time it's going to cover the same distance, because the velocity will more or less remain the same. But this time we have got x. Now this is something which is just a replica, but the only thing is you are going to talk about the mirror part, mirror image. So this is minus of ct, because it's on the other side of the x-axis or the origin. We are going to do a similar derivation here. Y is equal to 0, z is equal to 0, and time. So that means that we can again calculate x prime, which is equal to a, okay, into, you know, so you check this. Okay, let's just not lose track here. I see a into x minus vt, right? So let me write down this again. This is coming from the original expression. Okay, we are not going to change anything here. We are getting it from x minus vt relation, which we have already seen before. Okay, so a into x minus vt. So we have got a, and what is my x? X is minus of ct minus of vt. Okay, this is pure derivation, so you have to be very careful when deriving it. I can take out the minus common, a, and then t I can take common, so this would be this into c plus v. Okay, we have got one relation here. Similarly we can actually find out t prime, and t prime, this what we can do is dx plus f of t, and x is nothing but minus ct, so minus ct plus f of t. Here also let's take out t common, and I can just have it as minus dc plus f. Let's mark this as equation 7. And then again we are going to use the same logic as we've used in the previous problem in the event 1. Again, yeah, this is equation 6. No, equation 6. Okay, no problem. I will take this as equation 6. Yeah, I think we have done till 5, correct. So again we have got x prime is equal to minus of ct prime, because whether you consider the prime frame or the unprime frame, in both the cases this will remain the speed. But then the negative sign is important here. Therefore we can just replace it in this expression. This is x prime is equal to minus at into c plus v. So in place of x prime I can write it down as minus of ct prime is equal to at, there is a minus here, into c plus v. So this minus, we can just get rid of it, okay? And then we have a relation which is ct prime is equal to a into c plus b, okay? Let's mark this as equation 7. So again, just like before, what we can do is we can actually take relation 7 and then divide it by relation 6, and this will give us, on the left hand side it is ct prime, and for the equation 6 it is t prime is equal to, on the left hand side of equation 7 is a into c plus v, and on the right hand side this is t into minus of dc plus f. Okay, this is an at here, sorry, missed out on that t. So there is an at, so this t and this t gets cancelled, this t prime and this t prime gets cancelled. What we have here is c is equal to a into c plus v divided by minus of dc plus f. Just check the steps, keep on doing on your own. I think it will be important. You have to practice it once before exam, otherwise you will get confused. खाली देख के आओगे तो याद नहीं रहेगा शायद, तो एक बार आप लोगों को प्रैक्टिस भी करना है. तो क्रॉस मल्टीप्लाई इट, माइनस डी सी स्क्वायर प्लस एफ सी इज इक्वल टू a into c plus b. Let's mark this as relation 8. So you can see we are getting so many relations, but then we are actually slowly but surely reducing the number of variables. Okay, we already know b and a is there connected, so we have got rid of b. We are trying to get rid of, or trying to calculate d, f and a. We can do it if we have three equations, right? Mathematically, if we have three unknowns, in this case we have got d, f and a. These three unknowns, if you want to calculate, you should have three equations. So we already have two equations. We need a third one to solve it, okay? So let's consider one more event and we will name it as event 3, okay? So the next is event 3. अभी x axis के दोनों तरफ तो ले रही है. What happens for the third event? In the third event, what we are going to do is we are going to consider the event to be along the y axis. Okay, so maybe I'll draw this again. So this is there, this is there, but this time the event is here, happening on the y axis, and I will write this down again as c into t. But then the equations will kind of change now. Okay, why? I think you can easily guess. The equations will change. How? See, x will become 0 now because there is no motion along the x-axis, right? There is no motion along the x-axis, but y will be distance now. Y won't be equal to 0, y will be ct because the event is at a distance ct on the y-axis. Z is equal to 0. If we had more variables, we would have included z also, but we don't need to. That's the beauty of maths. Therefore, when we write down the equation, we can simply write it down as x prime is equal to a into x minus vt. But now you see x is equal to 0 for this event, so this would be nothing but this is 0, so this will just remain as minus a v t. That's the relation. And then y prime we know is equal to y, because the original relation y prime and y are still remains, but then y is equal to ct, that means y prime is equal to y is equal to ct. Whatever is y, the same will be with y prime. And then z is equal to 0. Let's take it for t prime. So t prime is equal to dx plus ft, and we know x is 0, so this will just remain as f into t. So that's the value of d. We have found one relation here. Okay, now if we basically consider a three-dimensional system, and if we just write down a general equation, okay, if we just write down a general equation, so what can I do is I can write down distance from O prime, if I consider the prime coordinate, okay, is, let's say, what will be the distance if I consider the vectorial representation? It will be like this. d square, maybe this is the distance, we are saying d is the distance, d square is equal to x prime square plus y prime square plus z prime square, right? So if you consider vectorially, if you want to find out the position of a point, okay, and if you know the x, y and z coordinates, you can actually find it out using this particular relation, right? We already know it, and we are going to just replace whatever we have seen here. What is my x prime is minus a vt. So if you square it, it will be plus, so I can just write it down as a square, v square and t square. Once we finish it, we will appreciate why we are doing this step. Plus, okay, y prime square, so y prime is ct, so I will just write it down as c square t square, and z is 0, so z prime is 0, so this is 0 square, so I don't need to consider this. Okay, now also, okay, this is something which is vectorially done. Also we know that if you actually want to know what is the distance, okay, maybe I can just write it down, or I won't write down d as distance. I think d, if I write it down, you'll get confused. I'll just write it down as distance square. Okay, so here also, if I just find out the relation again, I know that distance is equal to nothing but ct prime. This is something which you already know because the speed is same in all the distances. So I can also write it down in ct prime. Now previously I did not use this particular idea because we didn't needed it, okay, because we had a relation along the x-axis, so we could solve it. Now we actually don't have an x-axis, we have a relation along the y-axis, so in order to make it convenient, we are going to do it. So ct dash square, that means I can just simply write it down as distance square is equal to c square t prime square. And what is my t prime? So we know t prime is equal to f into t, so that means this would be equal to c square. T prime is f into t, so it is f square t square. So this is also a relation for distance square, this is also a relation for distance square, so we can actually equate them, and this is what we are going to do, right? So therefore we can write a square v square t square plus c square t square is equal to this relation. This is c square f square t square, right? So everywhere we can see that there is a t square here, this is a t square, this is a t square, this is a t square, so we can just cancel them out, and we have got it as a square v square plus c square is equal to f square c square. This is our relation 9. Right, we have got one more relation. So how many relations we have? We have 3 relations, and from these 3 we can easily solve and find out what is the value of a, b, f and d. Okay, b we already know in terms of a, so a, f and d we can easily find out from these. So what we have is, therefore we have 3 relations. So everywhere it's a relation between a, f, okay. So a and f also is there, so it's just between a and f, so it becomes even more easy now. So we have from, let me just write down all the relations again, all of you please check if we have done it, so you should be able to see. We have from 5 relation 5, from relation 8 and relation 9. Just not to confuse you, let's get back. What is 5? This was the relation at the end of event 1, whatever we got. Relation 8, this is the relation which we got at the end of event 2. And relation 9, this is the relation that we got at the end of event 3. So we've considered 3 different events and we have found out 3 different relations, right? What are these relations? Let's just write them together so that we can easily understand that how we can solve it. So it is dc square plus fc is equal to a into c minus v, that was 1, and the second one was minus dc square plus fc is equal to a into c plus v, and the third one that we got is a square v square plus c square is equal to f square c square. So you see, you have to do so much of maths and so much of algebra so that you are actually landing with the relation. Okay, so this is your relation A, This is your relation B. I'm just marking them new numbers so that we can solve them easily. And this is your relation C. Okay. So I don't want to continue because if I continue I'll take minimum 15 minutes here because I'm writing it on screen. So we will stop here, but then you can try it on your own. And anyway, I'm going to discuss in the next class how we are going to use these three relations to solve for D, F, and A. We have got a D, F, and A here. We have got a relation between A and F here. So we have got three relations, three unknowns. Mathematically, 100% we can solve for D, F, and A, and then we can find out what is B, and then we will replace whatever we find in the original relation here, AX plus BT and DX plus FT, and that relation would be called as Lorentz transformation. What's the difference? We are considering three events where we're saying that the light particle is traveling or the photon is traveling, and we are measuring the distance in terms of speed of light. So this is CT, this is minus CT, and this is CT along the y-axis.